Left off last time. We were in chapter 7, flow over external surfaces, and we finished the first half, which is flow over flat plates, and now we're moving on to the last half of chapter 7, which is flow over cylinders. So we discussed this a bit last time. We looked more at the fluid mechanics part of the flow over a cylinder, and the picture looks something like this. The Reynolds number is based on the diameter of the cylinder, of course. The flow around the cylinder starts off laminar, may or may not transist to turbulent, and ends up on the backside typically with a wake region. So that creates convection heat transfer. So our object, like chapter 7, the object is how do we find the convective coefficient H? We're going to look at H bar, the average coefficient over the total cylinder surface. And we can't really do that analytically. So we rely on experimental observations. These experimental observations lead to what are called empirical correlations. Empirical means based on experimental observations. The word empirical. So the one we're going to use out of our textbook is called the Hilbert equation, equation 752 in the 8th edition. In the 6th edition, it's a different number equation, but you'll find it's labeled the Hilbert equation. This is what it says. The average Nusselt number based on diameter is the average H times the diameter divided by the thermal conductivity, Nusselt number, equal a constant Reynolds number, D, raised to the m power, Prandtl number to the 1/3. Good for Prandtl number greater than 0.7. As we mentioned, that covers a lot of fluids. All the properties in here are based on the film temperature, which is the average of the surface temperature and the free stream temperature. Now, those constants, C and M in that equation, are given in table 7.2. Table 7.2, the first column is a Reynolds number range. I just took one out of there. So there's different Reynolds number range, maybe 4,000 to 40,000. 40,000 to 400,000, 400,000 to something else. There's various Reynolds number ranges given in table 7.2. So the first thing you do in a problem, of course, is you find the Reynolds number. Then you go to table 7.2, get the constants C and M, put them in the equation up here and calculate H bar, and put that H bar down here to get Q. This is the total Q. Diameter D, length L. So if this is the cylinder here, my pen, diameter, this is the length L out of the blackboard towards you. It's the length of the cylinder right there. So it's very straightforward. And that is for circular cylinders. Now, for non-circular cylinders, okay, there's different pictures in our textbook. I'll just mention a few. First of all, we use Hilbert equation. So, Nusselt D C Reynolds to the M equal, let's get equal sign there. So it's the same as that guy there. That's table 7.3. So here's table 7.3. Now, by geometry, we mean, what is the non-circular cylinder? Is it square? Is it hexagonal? What's the cross-section look like? So the textbook, I'll put a few here. I'll put 2 here. Textbook has 5, I think, in there. So 1 is a square tube, D, D, from the top to the bottom. Okay, and then there's another one, which looks like this, rotate it 45 degrees. Flow hits here. This is D. And there's other ones here, there's more. So I've just showed you the first 2 in that table for square tubes. And then let's just take this guy here. This is from 5,000 to Reynolds number from 5,000 to 60,000. 0.158. 0.66. So you look at your geometry. Okay, let's say it's a square tube. Okay, is the velocity of the fluid coming in normal to the surface? Here, yes. Put these constants C and M in here for the Reynolds number, range 5,000 to 60,000. Down here for this picture, there are other C and M values. Now, don't get confused, of course. This D in here does not stand for diameter, obviously. D does not stand for diameter. It stands for dimension. The dimension, top to bottom. Dimension D, top to bottom. That's how you define D in those pictures. Like in fluid mechanics, in my video lectures in fluid mechanics, you've got a funny car in drag racing. You've got a tractor-trailer truck. You've got a motorcycle. They all have Reynolds numbers. They all have Reynolds numbers. What do you define the Reynolds number as? The diameter of the wheels? I don't think so. The diameter of the headlights? No, that's nonsensical. The diameter of the guy's helmet on the motorcycle? Obviously not. You got to pick something for the Reynolds number. Well, what they do, tractor-trailer truck, the road where the tires touch it to the top of the trailer body. That's what they use for Reynolds number. Funny car, NHR drag racing, where the tires touch the ground to the top of the funny car. Motorcycle, from the tires touch the ground to the top of the helmet, motorcycle rider. That's what they define in the Reynolds number. So here, what they do, same thing, top to bottom. Top to bottom, top to bottom. Why top to bottom? Why not the width? No, it's top to bottom. So when you look at something straight on, top to bottom, that's what you define the Reynolds number. Okay, well, back to heat transfer. Very, very simple, very, very simple compared to flat plate. You've got one equation. Now, this is the same equation. All you do is either go to table 7.2 or table 7.3 because ask the question, is it a circular tube or non-circular? Once you get C and M, put them in the Hilbert equation, get the H bar. Once you get the H bar, put it over here. Except let's put down, well, we'll do it in just a minute. You got to watch those areas. You got to watch these areas right here. Now, there are 3 equations given in that chapter 7 to calculate H bar for a circular tube. There's 3 different equations. One is the Hilbert, one is Dukakis, one is Churchill. he says that there's a little better one than this, which is Dukakis. It's a little better. And then there's another one, Churchill, which is even better yet. And what it is where does this come from? I think Professor Hilpert, Germany, he published this. You can check the references in the textbook. He published this in 90 years ago, 1933. Yeah, 1933, and it's still in a textbook published in 2018 or 19. Wow. Wow. 1933. 1933. Before World War II. The instrumentation was nowhere near what it is now. Nowhere near what it's now. The Dukakis equation. It's a little more complicated than this. I'm not going to put it on the board. A little more complicated. It covers a wider range of properties, probably, I believe it does. Early 1970s. Early 1970s. Published. That means the data is taken maybe 1968, 69, 70 before it's published. Then you got Churchill. Now, Churchill's a really good equation. You don't need a table. It's one big, long, complex equation. You can program it. You don't need a table. One equation covers a wide range of properties and Reynolds numbers. Mid-1970s. And you say, well, this textbook's published 2018. Where's the 2020 or 2015 equation? No, there is none. The latest one they published is mid-1970s. You see, it takes a lot of money to run experimental data program. You dedicate laboratory space. You've got 3 or 4 technicians. You've got some young engineers to reduce the data. You've got secretaries to get ready to publish the paper. It takes a lot of money. So you got to find someone that's going to fund that. I don't know. Why it hasn't been done? I'm not sure. But I do know, I think, why the 2 other ones, this is 1933, then there's an early 1970s and mid-1970s. You know what was going on then. In the mid to late 60s, there was a race to the moon. Oh, yeah, NASA, big time bucks. That's how, yeah, NASA dumped tons of money in. DOD, oh, they're worried. Cold War, oh, yeah, tons of bucks. Well, it takes something like that to pump money into this to get new data. And so probably there hasn't been that big of a push to get new data. People say, hey, Churchill equation, that's fine. Let's use that one, mid-1970s. You know, we'll use that. And by the way, the author in the textbook says, now just so you know, he says, these correlations aren't, they're accurate to within 20%. Okay, he says that. They're accurate to within 20%. Okay, so you have to understand, don't give someone the H bar value here. H bar is 205.679826. No, who are you kidding? It's accurate to only 20%. How about round off to 3 sig figures maximum? So, you know, don't get too carried away. Sometimes spreadsheets allow you to get carried away like that. Yeah, no, not the truth though, okay? All right, so, conclusion. We're going to use this equation for both of these guys, even though it's dated back in 1933. In the real world, you'd probably use Churchill, the one equation that covers a wide range of properties and Reynolds numbers and so on and so forth. But we're going to use these 2 guys in our class, which means we have choices, table 7.2 or table 7.3. Okay, so let's look at a circular tube. A circular tube that I've got as an example, I think it's 10 centimeters in diameter. Let me just make sure I've got that down here. Yeah, 10 10 centimeter diameter. We also know that the fluid is air. We know that the fluid approaching the cylinder, T infinity, is 300 K. The cylinder TS surface temperature, 500 K. T bar, well, let's just label it T film. T film is T average, 300 plus 500 divided by 2, 400 K. Properties at 400 K. Let's see what else. V is 13.2, approaching velocity 13.2 meters per second. That's about 30 miles an hour. So use Hilbert with table 7.2. Table 7.2. Okay, first thing we do, calculate the Reynolds number, of course. Kinematic viscosity, back of the book, appendix at 400 K, air. And we get the Reynolds number, we know the velocity, we know the diameter. We get the Reynolds number 5 times 10 to the 4th. 50,000. Go to table 7.2. Reynolds number in the range 40 to 400,000, 50,000. C 0.027, M 0.805. H bar D over K. C 0.027. Reynolds number to the power 0.805. Prandtl number to the 1/3. H bar comes out to be 48.9. Q prime. I don't know the length, so I do Q prime. H bar pi d Ts minus T infinity. The area of the tube is pi dl. So Q prime divide Q by L. So the area then, the area per length is pi d. 3072. Watts per meter. Okay, so that's how we do it. It's very straightforward, very simple. Now, square tube. I'm going to take the one where the velocity V is normal to the flat surface. Everything is the same. Given Ts, given T infinity, given the velocity, given this air, everything is the same. So the Reynolds number is the same because what's it based on? The top to bottom of the square tube, which is D, which is 10 centimeters. 5 times 10 to the 4th. Just by the way, sometimes in that chapter, when he works example problems in the chapter, rather than Hilbert, he might use Zukakis sometimes. So, no matter what, for homework or a midterm, always use Hilbert. For homework or a midterm, always use Hilbert. Even though the author in chapter 7, for some example problems, uses the Zukakis equation to find h, we're not going to use that more complicated equation. Okay, back over here, table 7.3, we've got a Reynolds number of 50,000. Yep, falls in here. So I know C and M, 0.158 and 0.66. So let's see, we've got 0.158. Reynolds number D raised to the 0.66. Prandtl number to the 1/3. Solve this for h bar, and we get h bar 59.6. Put that in Q prime, and we get h bar. Now, of course, you've got to get the right area in there. And the area, there's 4 sides, top, bottom, left, right. So the area now is 4D. The area per unit length is 4D. Okay, so I think that takes care of that. Yeah, it's very simplistic. It's extremely straightforward how to find the convection heat transfer. Okay, so before I erase that, any questions on that then? Okay, I'm going to save this. Yeah. Now, we're going to look at how those values of C and M were determined. Because it's just interesting to see how engineers come up with something like this. How did they do this table? How did those values, where'd they come from? Okay, well, in the textbook, and I'll put this on the board, a picture of it, but I'll give you, this is example 7.3 out of chapter 7. So it's out of chapter 7. Front and back. I think that's 4. I'll give you 1, 2, 3, 4, 5. So, as I said, the Hilbert equation and all of these correlation equations, they came from experimental observations. So this example kind of explains how they got the H values. So they have a picture there, which is a wind tunnel. So the air is coming in the wind tunnel, drawn in by a fan at the right-hand side. They put the cylinder in the wind tunnel. Diameter D. Well, when I taught this the same textbook several years ago, I had a student after class ask me, she said, "Professor Biddle, I'm doing a senior project. do you think I can do a senior project? Because she read this thing, in this example. She said, can I do a senior project like this example 7.3 in the textbook? And I said, yeah, I don't see why you can't. So we had a smaller wind tunnel in aerospace engineering at the time we could use. And it was about 1 foot wide and 8 inches high. A smaller wind tunnel, not their big one they have in the wind tunnel lab. And so she said, okay, can I use that? And I checked with aerospace, and they said, sure, not a problem. You can use a small wind tunnel. So she got a aluminum cylinder, like this picture here is an aluminum cylinder, not aluminum, it doesn't say what it is. But she got an aluminum cylinder, and she mounted that in the wind tunnel, so it was 1 foot wide from side to side. And then she measured the air temperature approaching the wind tunnel with a thermocouple. So that gave her T infinity. Then she put a pitot tube at the center of the wind tunnel, and that gave her the velocity V. And then she put a thermocouple on the outside of the cylinder. That gave her the surface temperature. Actually, she put 4 thermocouples, top, bottom, front, back, and she averaged them to get a good average around the whole surface of the aluminum cylinder. She bored a hole through the cylinder. And then she inserted what's called a cartridge heater. It looks like this, with 2 wires coming out, DC power supply. She inserted the cartridge heater inside of the cylinder to provide power. This cartridge heater gets hot, which means the TS gets hotter than T infinity. She connected the leads to a power supply and then obtained the power into that from a watt meter. So that's how she got how many watts came into the cylinder. And then she started to calculate things. She set the velocity to a certain speed, measured all these guys. For any one run, she got the Reynolds number, V, D over nu. She knew those guys. Pitot tube, vernier caliper gave her diameter, properties of air at the film temperature, Ts plus T infinity divided by 2. Then the power that came in watts was equal to, right here, H bar times the area. The area was pi d L, that's the area. Ts minus T infinity. She knew it, she knew it, she knew it. She knew it, she knew it, she knew it, she knew it. She knew it, she knew it. You back out H bar from that equation, and then you get the Nusselt number, average, based on diameter D, H bar D over K. So now she had the 2 dimensionless parameters, Reynolds and Nusselt. And she did that. She changed the velocity. That's what she did. You change the velocity and you get different Reynolds numbers. So now she, of course, had a table of Reynolds number D versus Nusselt D. Changed the velocity, got new Reynolds numbers. Then she plotted it. So let's put that right here. see where Nusselt D comes out. Okay, I think I've got it right here. Oh, okay. So, Nusselt versus Reynolds. Plotted on log-log paper. Log-log paper. When you plot it on log-log paper, you end up with, if I get this right, this is 1 times 10 to the minus 2. One times 10 to the minus 1. 1 times 10 to the 0. So, this was for air. She changed the velocity, and so it looks something like this. Here's the experimental data points. If you want, you can draw a line through them. And she did that. How does an engineer know to plot the data, Nusselt versus Reynolds number? Why not plot h bar versus velocity down here? It's reasonable. She changed the velocity. Why does the engineer who takes experimental data end up deciding to plot the data Nusselt versus Reynolds? Well, you guys have been through that in fluid mechanics. Dimensional analysis. What's one of the most powerful things about dimensional analysis? Well, it takes a bunch of variables and lumps them together into what are called dimensionless parameters, which then gives you, the investigator, the experimenter, an idea of, you know what? Rather than plot h bar versus v, I'm going to plot dimensionless Nusselt number versus Reynolds number. Okay. Say, well, could you plot it on, well, let me just wait a second, I'll tell you why then. Now here's the deal. Maybe I'll tell you now. The first thing you would try and do is plot this thing on rectangular paper. You know, so if you were lucky, you would get a straight line of rectangular paper. What does that mean? That means it's a linear variation. Okay. If that didn't work, you might try and plot your data on semi-logarithmic paper. If it turns out a straight line, that's exponential variation. If that doesn't work as a straight line, you might try and plot your data on a log-log paper. If you get a straight line there, lucky you, it's a power law. Here's the power law. Y equal a constant, x raised to a power. If you get a straight line on log-log paper. Well, I don't have a straight line. I've got a curved line on that paper. That's okay. We'll play this game now. You know, if I take these two data points right here, and this is 4 times 10 to the 4th, and this is 4 times 10 to the 5th, you know what? I can just about draw a straight line through those 2 points, and it looks just about like my dashed line. But I can only do that in this range right here, 40,000 to 400,000. And if I would measure the slope of that, 0.805, I could take a ruler, 4 inches divided by 5 inches, 0.8. If I use log paper and the logs are the same scale on both x and y axes. Now, how do I get C? Well, you extend that line, extend that straight line all the way down to where Reynolds number equal 1 on the log axis. And that is C, 0.027. That's the game they play. They break the curve down into a number of straight line segments between various Reynolds numbers. They get the slope, that's M. They get the intercept at Reynolds 1, that's C. They put the table together like this. So that's where this thing comes from. Sometimes these things are like magic, like, well, where'd that thing come from? I know, I know. It's nice to know, though, to explain to someone where it came from. So we take this, break it down into a bunch of straight line segments, and get a C and M for each straight line segment, and then publish the table, table 7.2. Okay, so, well, by the way, she did that, and she got the graph and everything. She came within, I think it was like 15 to 18% from what these numbers were. Pretty good for Cal Poly Pomona. This, this is not JPL. This is not Caltech. This is Cal Poly. We were really pleased with that. So her senior project was a success from that point of view. So good for her. She found that in the textbook and said, Professor Bill, can I do my senior project based on that? I said, yeah, it'd be great. Now, I took, this is from a different textbook, and I'll put on the board what it looks like, but this is another graph that's interesting. So this is a graph just about like this one that we're talking about here, almost identical, and this is what it looks like. Log paper. Here's the this is Nusselt bar D divided by Prandtl to the 1/3. And this is the Reynolds number D. All they did is they said, I'm not going to plot Nusselt versus Reynolds. I'm going to put that Prandtl number on the left-hand side. So it's Nusselt bar D divided by Prandtl to the 1/3. So that's why the y-axis is that. Now, reference 19, those people experimentally used water with a diameter of the tube 0.0254 meters, which is 1 inch. 1 inch tube, water. They changed the velocity and they got these data points. Reference 20, used oil, diameter 1/10 to 2/10. So they got oil. That's oil. Then 2 other authors used air with different diameters. They got data that looked like this. Now there is data scatter on here. There's data scatter because of uncertainties. So they've got two dashed lines which show the data scatter, and it says plus or minus 15% on the right-hand side. So these data points all fall in a band, and that band has a width of 15% plus or minus. So again, as we said earlier, don't take these numbers to be super accurate. They're within generally 20%. Okay. Then he said, if I go from a Reynolds number of 3 to 100, I'm going to draw a straight line through those points. That's what he did. It's at the top in the box. And he says, if I do that, the slope of this line, 0.4. And where that line crosses Reynolds number equal 1, here comes the value of C, 0.82. So he said, between these two Reynolds number, the equation is Nusselt bar D over Prandtl to the 1/3 equals 0.82 Reynolds number D to the 0.40. So again, that's how they got that equation. What's it valid for? Only between Reynolds number of 3 and 100. Then they could curve fit it to a straight line here and a straight line up here. So that's, now, this student here at Cal Poly, she just took air at one diameter, 4 inches. This data, you know, you can see the different diameters, the different fluids, water, oil, air, all the data, water, oil, air, every velocity, every diameter falls on what? One single line. Powerful? Are you kidding me? Powerful? It's unbelievable. 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 Well, no, I take it back. You can believe it. I'll tell you why you can believe it. Air, water, oil. You've seen it before. Magic. Fluid mechanics. Oh, yeah. Thank you so much, Mr. Moody. You're a wonderful man. One curve. For what? All laminar flow. For all fluids. For all diameters. For all velocities. One curve. And if you watch my fluids videos, you know I said that, the guy goes out in the lab and comes back 2 years later and says, here it is, boss, what you asked for. The boss says, well, is air in there at 50 feet per second? Yeah, page 921, here, right here. Is water in here for a diameter of 1 inch and a velocity of 50 feet per second? Yeah, boss, it's here in page number 1052. Then the other guy comes into the boss and says, you know, boss, I've been gone for a while, but here's what you asked for. Laminar flow. Boss says, well, 1 page, he says, where's the one for air with a diameter of 1 inch and a velocity of 50 feet per second? You say, here, boss. Well, then where's the one for oil, velocity of 15 feet per second, diameter of 1 foot? Here it is, boss. Boss says, you telling me that one graph is good for every fluid, every velocity, every diameter? I said, yeah, boss. He says, hey, Joe, come here a minute. How many pages do you have? 10,560. And how many does Phil have? 1? I like Phil. I like Phil a lot. No, the power of dimensional analysis. Without that, you've got tons of pages. With the power of dimensional analysis, I don't care if it's heat transfer. Is this log-log? Of course it is. I don't care if it's heat transfer or if it's fluid mechanics. Wow. Is that something? And what's this guy here? F equals 64 over Reynolds number. What is that? 64 Reynolds. Does that look like a power law? Y equal constant times x raised to a power? Of course it does. If it falls as a straight line on log-log paper, it's a power law. Yeah, that's right. So, yeah, interesting story about that. Whether it's heat transfer here or fluid mechanics here, we love to plot our experimental results on dimensionless parameters. That's the key. Okay, good stopping point. So we will continue. We'll start chapter 8 then on Monday, starting chapter 8 on Monday.